Right, question 1. All you have to say is that entropy is a measure of the dispersal of energy in a system. It's as simple as that, and you need to know that, you need to be able to say it, but you don't need to think about it anymore, because we think of it in particle terms, but that's the fundamental explanation. So part B, what you need to be able to explain is that the more disordered the particles are, the more dispersed their energy will be, and therefore the higher the entropy will be. And that's really all you have to say. So that's just, I think it helps if you have this picture in your head of the idea that if particles are all have pretty much fixed positions like in a solid, because they have very little freedom of movement, the energy that they have with them is very organised and contained as well. So that's a low entropy state. If you imagine, on the other hand, particles whizzing around in the gas phase, they're all just doing random stuff, constantly redistributing themselves, and so the energy they carry with them likewise is in a much more dispersed state than it would be in the solid. So you just need to make the connection that disordered particles equals highly dispersed energy equals high entropy. Now part C, what this is getting at is the idea that in the universe as a whole, entropy is always increasing. That's just a fundamental principle. So everything that happens in the universe is always associated by an increase in entropy when you look at the universe as a whole. Now that does not mean that within a localized part of the universe, like what's going on in a test tube, for example, it doesn't mean that entropy necessarily has to increase within the test tube. You can get a process like crystallization, for example, where the entropy change is negative within the test tube, but if that's accompanied by heating, which it would be, as you form the bonds when it crystallizes, that heat spreads around the universe, so it disperses the energy, and overall the entropy change can be can be positive in the whole universe. But what this is saying is, if within the system the entropy change is negative, is that a good or a bad thing? And in terms of contributing to the idea that overall the entropy change in the universe must be positive, obviously it's not a favourable thing, so it will make the change less favourable. We'll come back to this idea in a more sort of concrete way when we look at free energy. But basically all you have to say is that a movement to a state of lower entropy makes an unfavourable contribution to the overall change, but it doesn't mean it's impossible. It just needs to be outweighed by a favourable energy change. And that leads on to part D. What's the other factor? And the other factor is energy, or you could say enthalpy, because those two things are pretty much interchangeable. So you can say that the other factor that controls what's the most stable state, in other words, which direction a reaction will go, is the enthalpy change. So enthalpy change and entropy change, and we'll see how free energy brings those together later on. Question 2 is just about using this simple idea that the more disordered the particles are, the higher the entropy is, to think about various kinds of processes. So boiling water to create steam, you're going from a liquid, which is a reasonably ordered state, to a gas, which is a much more disordered state. So if you wanted to write an explanation as well as an answer, and we won't do this for all of them, but we could do it for a couple of them, what you would say is that change from liquid to gas means that the particles, or molecules I guess we can say in this case, become more disordered. And if the particles become more disordered, that means that delta S is positive. And we do the same kind of thing for all of these. So for B, crystallization of a salt from a saturated solution. You just picture that in the solution, the ions from the salt are moving around randomly within the solution, so they're highly disordered. But in the crystal, they're all locked together in fixed positions, so that's much less disorder. Okay, so for that one, we've got solution going to a crystal. Okay, that's a change from separate particles in solution, which are therefore disordered, to, if you like, fixed positions in the crystal, which is much less disordered. Which means that delta S is negative in that case. If you were worrying, shouldn't we worry about what's happened to the entropy of the solvent as well as the solute? The answer is absolutely yes, but not at A level. If that were to come up at A level, you just focus on the solute. But in the real world, yes, that would be a real issue. C, formation of oxygen from ozone. So if we think of this reaction, ozone is O3. So if that gets converted into normal oxygen, we're going from 2O3 to 3O2. And this is a case where all we have to say is, obviously it's still gas going to gas, so we haven't got different states to think about, but what we've got is an increase in the moles of gas. So we're going from 2 moles to 3 moles. Increase in the moles of gas means that there's more disorder being created by the reaction, and so delta S is positive. And then if you carry on, sodium metal with phenol, that's actually not a reaction you have to know anymore, so this is an outdated question, but the reaction I can tell you is this, just so that you can think about it. Sodium plus what we're reacting it with? Phenol. Okay, so this is actually a redox reaction. It's very similar to the reaction that happens between sodium and water, because you can see it just produces hydrogen gas. So it doesn't matter about the reaction, all that matters is that you can see that you just have solids to begin with, but one of the products is a gas. So the gas produced means that there's an increase in the disorder of the system, and therefore delta S will be positive. The next one, hydrogen chloride to hydrochloric acid. Hydrogen chloride in its pure state, remember, is a gas. It's just a simple molecular gas. It's only when it dissolves in water that it forms hydrochloric acid. So we're talking about this process, and that's going from highly disordered gas to a much less disordered solution state, because it's now a liquid, so delta S will be negative for that. Part F, melting cheese is just going from solid cheese to liquid cheese, so the cheese molecules, if you can have a cheese molecule, are more disordered in the liquid cheese than they were in the solid, so delta S will be positive for that one. Formation of a planet. Well, planets form by sort of gas, interstellar gas if you like, under the influence of gravity, coalescing to form a body which, depending on what sort of planet it is, may be itself gaseous or maybe liquid or solid, but the important thing is that it's focused in a much restricted volume, and therefore that's a much more ordered state than when the gas is all spread out everywhere. So delta S is negative for formation of a planet. And then we have this reaction of ammonia and hydrogen chloride. So these are both gases, but they're forming ammonium chloride, which is a solid. So you can see the moles of gas this time are decreasing. So we're going from highly disordered gas to much less disordered solid, so delta S will be negative. And finally we have glucose dissolving in water. So C6H12O6, could be glucose or various other sugars, just dissolving in water to form a solution. And again, you can see that's going from a very ordered state where the molecules all have fixed positions in the crystal to a more disordered one where they're wandering around fairly randomly through the solution. So it's going to a more disordered state, so delta S will be positive. Okay, so those kind of questions are fairly straightforward if you can just picture the particles doing what they're doing, and most commonly you get gases involved. If there's a change in the number of moles of gas, then you can straightforwardly predict delta S from that.